On October 28th, 1707, a survivor described the sea rising like a wall of fire. That was the last time Japan's Nankai Trough ruptured in full. That was 317 years ago. The typical cycle runs from 90 to 150 years. The trough is not just overdue, it has been silently building strain for more than double the expected window. And now, seafloor instruments are picking up signals that scientists cannot ignore. A single diary entry from 1707 records the sea turning to flame and villages vanishing in darkness. That night, the entire Nankai Trough, spanning hundreds of kilometers from Suruga Bay to Shikoku, ruptured as one. The Hoei earthquake, estimated at magnitude 8.6 or higher, sent a tsunami more than 15 meters high into coastal plains, leaving evidence in boulders tossed far inland and sand layers buried beneath rice fields. For centuries, this event stood as the most complete rupture in Japanese records, with devastation stretching across every segment of the megathrust. But the Nankai Trough does not always break in one piece. In December 1854, two earthquakes struck less than 32 hours apart. The first, the Ansei Tokai event, ruptured the eastern segment. The second, the Ansei Nankai, tore through the western half. Together, these paired shocks released energy nearly as great as 1707. The pattern was different, and each segment failed in rapid succession instead of all at once. Eyewitnesses described the ground trembling before dawn, followed by a second jolt and a wall of water the next evening. Tsunami heights reached 28 meters in some bays, and coastal towns were swept clean twice within 2 days. These events revealed a pattern now central to Japanese hazard science. The Nankai Trough behaves as a series of linked but not always synchronized segments. Sometimes, like in 1707, the entire fault gives way. Other times, as in 1854, one segment's failure triggers its neighbor in a cascade. Modern researchers label these as single or paired ruptures, tracking the boundaries. Tokai to the east, Tonankai in the center, Nankai to the west. Historical records, tsunami deposits, and even offshore boulders point to recurrence intervals of 90 to 150 years for each segment, with full-length ruptures appearing only every 300 to 500 years. The intervals are not clockwork, but the rhythm is clear. The Nankai Trough silence is always temporary, and its segments are never truly independent. Each past catastrophe resets the clock in a different way, shaping how risk is measured along Japan's southern coast today. Scientists in Japan have developed a way to turn centuries of earthquake records into a measurable warning system. The heart of their approach is the seismic gap metric, a number that tries to capture how much strain is currently locked beneath the seafloor, waiting to be released. The calculation starts with two pieces of data for each segment of the Nankai Trough: how long it has been since the last major rupture, and how tightly the tectonic plates are stuck together. This tightness is called interplate coupling, and it is measured on a scale from 0 to 1. A segment with a coupling of 0.8 or higher is considered locked, meaning almost all the plate motion is stored as strain rather than slipping quietly. To calculate the gap, researchers multiply the coupling ratio by the time since the last rupture. For example, if a segment is 85% coupled and it has been 170 years since the last major quake, the gap product is 144.5. This number is then compared to the average expected value for that segment, based on historic slip rates and recurrence intervals. If the result exceeds 1, the segment is flagged as a gap, meaning it holds more strain than it typically releases in a single event. Three main streams of data feed into this system. First, paleoseismic studies and historical catalogs provide the dates and sizes of past ruptures. Second, dense networks of GPS receivers and seafloor geodetic instruments supply real-time measurements of plate movement, revealing where the fault is locked or creeping. Third, observations of micro-earthquakes and slow slip events help refine the picture, showing where strain is being relieved without a major quake. By combining these sources, scientists can map the Nankai Trough's strain budget in detail, segment by segment. The coupling threshold is crucial. Only zones with a coupling above 0.8 are treated as locked and capable of generating a megathrust earthquake. Lower values suggest some strain is being released quietly, reducing the immediate hazard. But where high coupling and a long interval since the last rupture coincide, the alarm level rises. This approach turns a patchwork of old diaries, buried sand layers, and millimeter-scale GPS shifts into a single operational number, the seismic gap, that guides Japan's hazard maps and emergency planning. As data from seafloor instruments grows, this metric becomes ever more precise, but it also reveals just how much remains hidden beneath the waves. South of Honshu, a network of instruments keeps constant watch over the Nankai Trough. Each device offers a different window into the shifting boundary between the Philippine Sea Plate and the Eurasian Plate. The backbone offshore is DONET, the dense ocean floor network system for earthquakes and tsunamis. 15 GNSS acoustic nodes, anchored as deep as 5,000 meters, measure plate movement with sub-centimeter precision. By bouncing acoustic signals to surface ships, they map strain building up between the plates. The nodes are spaced 30 to 50 kilometers apart, so smaller features can escape notice, and rough seas sometimes scramble the acoustic link, causing real-time data to lag by minutes as it is relayed to shore. To catch the earliest signs of seismic activity, more than 150 S-net broadband ocean bottom seismometers line the seafloor. These OBS units record ground motion across a broad frequency range, from 0.01 to 100 Hz. They capture everything from tiny microquakes to the slow, rolling tremors that can signal a slow slip event. But each OBS runs on batteries that need replacement, so data sometimes arrive in bursts, not as a steady stream. Soft marine sediments can blur sharp signals, making it harder to pinpoint small or shallow events. Borehole pressure gauges and tsunami sensors, sensitive to changes as small as 1 centimeter, stand ready to detect sudden shifts in ocean level. These pressure sensors provide rapid tsunami alerts, often within minutes of a major quake. But their readings are reactive, not predictive. They only warn after a rupture has begun. On land, about 1,000 GNSS stations across Honshu, Shikoku, and Kyushu track crustal movement every second, measuring shifts with millimeter accuracy. Satellites equipped with INSAR sweep overhead every 6 to 12 days, mapping ground deformation. INSAR can spot subtle surface changes, but its signals are sometimes distorted by clouds or moisture. The land-based GNSS network cannot sense what is happening deep beneath the seafloor without help from offshore instruments. Engineers and geophysicists compare these streams of data daily, searching for patterns that might hint at the next great rupture, aware that even the most advanced tools have their limits. Between 2018 and 2023, a series of slow slip events quietly unfolded along the Nankai Trough. These episodes, lasting from several weeks to nearly 3 months, shifted the shallow plate boundary by 0.25 to 0.40 meters at a time. Each event spanned a stretch of up to 150 kilometers, with the largest in 2022 to 2023 showing intermittent slip over 280 days. Instruments recorded a local dip in coupling, about 5%, before values rebounded, leaving the deeper locked zone unchanged. While these slips relieve some strain, they account for only a small fraction of the total deficit building beneath the seafloor. Interpreting these signals has become one of the most urgent debates in Japanese hazard science. Some researchers, following the classic clock model, see the 317-year interval since the last full rupture as a warning that the fault is overdue. Their probability curves, fitted to the historical record, put the odds of a magnitude 8.5 or greater event at 30% within the next 30 years. Others turn to stress accumulation models, arguing that coupling ratios above 80% are a stronger indicator than time alone. These models suggest a 10 to 20% chance per decade, focusing on the physical state of the fault rather than the calendar. A third camp, emphasizing uncertainty, points to the wide confidence intervals, plus or minus 50%, and the complex geometry hidden beneath the ocean. For them, the only responsible approach is to communicate risk through scenario envelopes, not forecasts. Government hazard maps now bracket three main scenarios. A single segment rupture, limited to Tokai, would likely produce a tsunami about 4 meters high. A two-segment cascade, Tokai plus Tonankai, could drive waves up to 7 meters into Shikoku's bays. The full-length rupture, matching the scale of 1707, would send a wall of water 10 to 15 meters high across the Kii Peninsula and Tokushima. These numbers are not predictions, but they define the range of outcomes for which communities must prepare. The slow slip episodes sharpen the picture, but do not resolve the uncertainty. The envelope of risk remains broad, grounded in both the latest measurements and the memory of past disasters. Today, over 120 million people live within reach of the Nankai Trough threat. As sensors track invisible strain beneath the seafloor, every quiet year is a reminder. Preparedness is not a choice, it is a necessity. The next rupture is not a question of if, but when. Stay vigilant.